Hello, everybody. Welcome to my presentation. I'll start with the title itself. So this is about analyzing ride comfort in real time by integrating flexible body in white. So the model I'm using here is an old Ford Taurus model. So the body in white specifically, as a part of it, which is available online. So it's an IP free, as we say. And yeah. So let's start. First of all, with the motivation for multi-body simulation. So as we understand, multi-body simulation is a key method uh, for research and development of mechanical and mechatronic systems. You're quickly able to understand the system using MBD simulations. You can do dynamic simulation of complete systems, not just components, but complete systems using MBD simulations. It also acts as a integration platform for multi-physics simulation. So you could integrate things like integrate hydraulic systems, for example, using FMU approaches, or you can integrate flexible bodies from FE softwares like Abacus into an MBD solution package like SimPack in this case, or any control systems from MATLAB Simulink, for example. So it can act as an integration platform for multi-physics simulations. Um, Again, the next point, which is quite important, you can do sensitivity analysis and variant calculations, and this is especially because an MBD solver generally it's very quick, so it allows for DOEs and variant calculations. You can also use it throughout the complete verification cycle. So you can start off from a concept phase, and like for example, in this case, what's shown here, starting from a 1D torsional vibration model for a gearbox, and you can go on to creating a complete full fidelity or high fidelity gearbox, like in this case for a wind turbine. And it can be very useful for until the verification phase. Going to the next slide. So this slide shows a brief comparison between simulation and physical tests. Um, so basically, um, you can say that detecting problems already in or early in the design phases is possible for sure with multi-body simulations. While with tests, of course, it's impossible because you need a physical car. Um, so detailed variant studies, as I said, it's possible with MBD simulations, but it could be very expensive with the physical test. So depending on what sort of variants you want um, to vary, basically, it can be very expensive and time taking as well. Um, in terms of measuring motion and forces, it's obviously possible to place a sensor, in your virtual model anywhere in the system, and you can measure them. With the physical tests, it's only possible at limited places where you can do in the physical world. Um, Design changes are easy, of course. Um, it, it's a matter of seconds to minutes to change the design changes, do design changes in multi-body simulations. Whereas in physical tests, they are difficult and can be very expensive. Um, Analyzing misuse and abuse cases, again, it's possible in MBD simulations. Of course, part of it depends upon how robust the solver is, how can it solve and analyze misuse cases, but it's definitely possible in MBD simulations. But in the physical test, it's first thing, it's very difficult, or it can even be impossible to do in certain scenarios. But again, what we are seeing, what we have seen in the past is it's almost always required to do physical tests for subjective feel of a car. Going on to the next slide, which basically, so I've put this slide like a comparison between MBD simulations and FE finite element simulations, and the main differences are listed here. So what you want, so what you would see here is, so the modeling elements in MBD simulations are mainly bodies, joints, spring dampers, etc., like these. Whereas in FE simulations, you got material elements as the main modeling elements. Degrees of freedom an MBD simulation, an MBD model would generally have is from few to a few thousand. If it's a very high fidelity model, that's generally the maximum range, a few thousand degrees of freedom. Whereas in a FE simulation, the degrees of freedom go from a few thousand to a few million degrees of freedom. A typical calculation time, generally because of this number high number of degrees of freedom, is from seconds to hours in MBD simulations, where it can go from hours to days in FE simulations. Hardware requirements is very low for a multi-body simulation, and it's generally a multi-core workstation for FE simulations. Static analysis is possible and easy to do in MBD simulations, but it's possible and the main task of FE simulations. Dynamic analysis is also possible in MBD simulation, but also it's the main task of an MBD simulation. So you're running fully trans. So in most cases, you're running fully transient dynamic simulations with the MBD solver. Whereas with FE simulations, it's possible, but it can be very slow. It's generally very slow. Complete system simulation um, is possible and also the main task of an MBD solver. Whereas for FE simulations, it's possible, but also very slow. Material flexibility, it's possible, but generally in MBD codes, you're looking only at mainly the linear behavior of a flexible body. Whereas in FE simulations, this is of course possible and the main task, and also looking into non-linear flexibility, material flexibility of a body. The typical results in MBD simulations are positions, velocities, acceleration, forces, and torques. So the loads basically. Um, Whereas for FE simulations, the main tasks would be stresses and deformations. Um, of course, it's really important. So nothing in the real world is fully rigid. So it's of course it's quite important to include flexible bodies in MBD simulations for better and better accuracy. Depending upon your scenario, you want to include one or the other body or a couple of combination of bodies as flexible and rigid bodies. So to explain this, I've got a very simple example on my next screen, next slide. So this basically shows a simple plate, basically, which is resting on a spring. Um, and the other end, bottom end of the spring is basically excited, where so this is where an excitation is applied. And this is the excitation that is applied, which is basically like a position linear sweep starting from 5 hertz to 20 hertz, and it goes from 5 to 20 hertz in 20 seconds, basically. Um, so what you see on the left hand side is the same sort of plate, but modeled as a rigid plate. So there is no deformation or no flexibility on the left hand side. So this is a rigid model. On the right hand side, what you see is the plate where all the flexibility of this steel plate has been enabled. So all the eigen modes have been enabled basically. Um, and what I've also got on these plates on here, what you see, a little sphere is a sensor, basically a massless sensor used to measure the acceleration in Z at this end of the plate. Okay. Now if I go to the next slide. So when we measure these accelerations, what we see is if we compare the acceleration in Z, doing an FFT, so in the frequency domain, what you see is comparing flexible, which is in red, simulation, and the rigid body simulation, which is in black, shown in black here, is that not only you miss not only in this case you underestimate the response in terms of magnitude, but you also miss these critical frequencies basically because which are seen because of the flexibility of this plate. Yeah. So we see that it's really important to include the flexibility in this case when you're capturing the accelerations. Um, Obviously, to To include these flexibilities, I have to enable the eigenmodes of this particular plate here. So this is the list of the eigenmodes that I enabled. So what this means is that as compared to a rigid body, um, if I compare the degrees of freedom of this flexible plate with the rigid body, what you see is that the number of degrees of freedom that the model had when the plate was completely rigid was just one, which is basically moving up and down. Whereas in case of the flexible body, uh, of course, the motion had 1 degree of freedom, whereas plus that these 12 flexible body modes will also be included. So basically, we are running 13 degrees of freedom as compared to 1 degree of freedom, but we are getting more and more closer to the accurate results as well. So this again, more degrees of freedom would mean more computational power uh, requirement as well. So we'll look into this in the later part of my presentation. But next slide shows you basically some automotive MBD applications. So what you see on this slide um, is basically on the x-axis is we have put frequency from low to high, and then from on the y-axis we got amplitudes going from small oscillations to large oscillations, and we have divided this the different applications onto this chart based on amplitude and frequency. So obviously we have got handling, which is low frequency but higher amplitude uh, simulations. Ride quality, primary and secondary ride, which is sort of mid frequency simulation. And you can go up to higher frequency, which is NVH, driveline NVH can be categorized as higher frequency um, simulations. And of course, durability is sort of across the frequency range, but also higher amplitude. And what we wanted to do for this particular project was to run real time, to run and analyze secondary ride comfort. Okay, so we wanted to run real time simulation up to a secondary ride, which was basically around 50 hertz of frequency, right? I mean, the other part was also to integrate some control systems, but that's still planned for the future. But we have some control systems into the model, which I'll show you later on, which should also run in real time. So if I start off with the requirements of this sort of project, the main requirement was, of course, the easy coupling of the virtual world with the real world, which is the hardware, basically. And the important bit was the direct real-time simulation of complete systems, including flexible bodies and detailed force elements. So what it and also the another important bit was so we didn't want any model simplification going from uh, a full fidelity model going from offline simulations into real-time simulations. So this picture here on the right-hand side depicts what I'm just what I just said. So we had this an automotive database which was nothing but the collection of various different templates. So templates meaning some suspension type, some anti-roll bars and subframe and bodies, etc. So we created a full vehicle model, and the idea was to run the same complex model into offline mode. So run a simulation offline and see the results later on. And use the same model to run on a real-time simulator like this one. I mean, obviously in my office we have a static simulator. I'll speak about that as well later on. But the idea is to run the identical model both in offline mode and the real time and in real time mode, including the hardware in the loop. As you can see here, it's the complex model here, the same model. So we didn't want to go through this cumbersome process of simplifying the model to make it real time capable. So that's the whole idea, which simplifying the model kind of defeats the purpose, really, because if you have entered all the correct hard points and spring and damper and bushing properties files into this complex model, and you have validated the model in an offline mode like this one, you don't want to simplify it and then do another correlation to make sure that it still represents the correct complex model that you initially created. So we wanted to use the same model in offline simulation and real-time simulation. Of course, the main idea is to validate component interactions in complex mechatronic vehicle systems using software in the loop, driver in the loop, and hardware in the loop. And applications, as you can understand, one of it is obvious one is a driving simulator. The other applications could be engine test benches or ADAS setups, etc. Okay, so coming on to my next slide here. Of course, when you're using a full fidelity model, you're looking at quite a huge number of degrees of freedom, which are supposed to run in real time. What I've compared here, if you look here on this image, there are two methods of running a model in real time. One is you could characterize the suspension into some simple lookup tables, um, and then you can and to make sure that the model will run fast, because obviously it's a simplified model. But the attainable goal in this case would be only low frequency model testing, and the degrees of freedom of the complete model would be somewhere around less than 20. With SimPack, what we can do is have this high fidelity component model, which is not sort of simplified, and which means that the degrees of freedom of this model will be around or greater than 200. But the attainable goals would be model correlation up to high frequencies, basically. As a part of requirement, we wanted to include fully nonlinear frequency dependent bushings and mounts wherever required. We wanted to use high fidelity tire models as well. So an example of some tire models is given here. So TMEZ, which is a semi-physical tire model. CD tire is comfort and durability tire model. High fidelity, generally used for ride analysis. F tire from Kosin and Delft. So we wanted to use some high fidelity tire models, high fidelity bushings, and the full component based MBD model. Um, so so the application load cases, if we go on understanding which could be required. So again, on the frequency range, you have got from low to medium is going from handling to ride comfort, and high frequency will be NVH frequencies. And these were the load cases or the frequencies that we were interested in. So then after this, we started creating the model using a feature in SimPack called SimPack Wizard, what you see on this screen. And this is basically making use of an automotive database that I showed you in a few slides earlier. So we picked up the required templates for the correct suspension type for this Ford Taurus model, front and rear. It had got a front subframe as well, some steering system, springs and dampers. So basically the front, rear, and we only used a simple driveline model for this one because this was really more related to ride comfort. So the driveline was not really important to model as a very detailed one. And then so this basically now gives you an idea of what's actually the content of this model in the end was. So I mean, even if we did not require, we had some flexible side shafts. So this was based on SimPack's linear sim beam theory. So we included these flexible side shafts. We had this flexible chassis, which one of my colleagues from Abacus team, he created one for me for this Ford Taurus model, which I included into this model in SimPack. As I said previously, we had there was an option to include ABS and ESC systems using FMU, which was optional, but we included them anyway. So we are using an FMU for an ABS, so anti-lock braking system, and the ESC control system into this model as well. We started off with TMEZ tire model, which is a semi-physical tire model, which is a 4-point contact method in this case. So TMEZ, as I understand now, has been extended up to 28 contact method already now. I'm still to test it. And we had some nonlinear frequency dependent bushings as well. So overall, with this model and content, we had 264 degrees of freedom. That was the model which we used for real time. Now to next few slides, I'll show you what we did to this flexible body in white. to run it in real time, because that's really important. That was the most important part of this project anyway, to include flexible body in white and still be able to run it in real time to achieve a good real time factor less than 1, so that it runs in real time. I've taken an example of a lower control arm in this case. So I'm not showing you with respect the example here is shown is not of a body in white, because it could not be very clear. In this case, it's very clear. Now, so what you start with is a structural mesh in Abacus. We started with a structural mesh in Abacus for body in white. We defined the interface points, where it will connect with the rest of the MBD, with the rest of the assemblies. Then we define some couplings from these interface points to the rest of the structure or the surrounding structure. We define some retained nodes and the degrees of freedom for those retained nodes. Then in Abacus, we ran this reduction method, which is a very common practice to include flexible bodies from any FE code into MBD simulations like SIMPAC. So this is called Craig-Bampton reduction method. So we ran this analysis in Abacus, and the results of this, basically we pick it up and we create this FBI file, as we call it, or the flexible body file. This can be used straight away into SIMPAC. So now, if I go on to the next slide. So this is the whole process, an overview, what we applied onto the body in white, which was available in the flexible or the structural mesh of which was available in Abacus. So step 2 was the mode selection process, and this was really important. So in this case, if you look into the steps, so flexible node attachment markers. So wherever the attachment markers were on the flex body in white, were set up to include only necessary translations and rotations. So for example, for the damper top mounts, for the right analysis, you only would need a Z degree of freedom only. So and similarly for the other attachment points on the body in white, flexible markers. So eigenmodes were carefully chosen, modes that can have an effect on the right behavior up to 40 hertz. In this case, we chose 40 hertz. I think it could have gone further than 40 hertz were included. Now in SIMPAC, we have this special feature of auto eigenmodes option, and this we utilized it. So SIMPAC could tell us that whichever modes will have an influence up to 40 hertz of frequency. SIMPAC can calculate those, and we got this table. So there were 8 eigenmodes which were found by SIMPAC, and then we were able to create this reduced eigenmode flexible body within SIMPAC. So here I'm showing 2 most important modes, basically, which is torsion mode and the global torsion mode of the body in white, and the global bending mode of the body in white for this particular car. Going into a bit more detail, so this is an example of the damper top mount marker, the flexible marker on the body in white, attached to this node ID on the body in white, and then we enabled or disabled certain interface mode directions on this marker. The next, on the right hand side, what you see here is this auto eigenmode process which we used, or feature that we used for this body in white. And in the end, we were able to get these eigenmodes from SIMPAC, and we used these onto the and to go onto our real-time simulator. Okay. Once we had our flexible body in white into our SIMPAC model, we ran some dynamic simulations. So what you see here is a handling double lane change simulation. So this is still offline simulation to understand if everything is running fine. This model. So this is using our Simpac driver controller, which is basically a PID, advanced PID controller. So the measurements looked okay in this one. Next was to run this full vehicle model using the flex body in white onto a rough road. And once we made sure that the results looked okay, um, obviously we were interested into this model to uh, go on to the real-time simulator. Okay, and then what we did, so of course, this plot was quite an important plot for us to understand. So this also sort of tells you, apart from my previous very simple steel plate example, this shows you why it is important and what do we miss if we don't use a flexible body for this type of ride analysis. So this is the plot of from the damper top mount vertical Z accelerations. Um, one of the top damper top mounts. Um, so we can see here's a clear difference in accelerations captured at higher frequencies. So okay, it's okay until here, but from here around I don't know 12 and a half hertz up to 35 40 hertz, there was a clear difference, and a lot of content was missed if we were to use only rigid body in white for a ride simulation. So of course the red is rigid and the black is fully flex. So this is a fully flex body in white without the reduced eigen modes. Yeah, run an offline simulation. Then what we did was we used the newly created RT modes flex body in white. So the full flex body in white was using around 31 modes. RT modes flex was using 8 modes that Simpeg auto eigen mode feature generated for us. And the rigid body was still using the flex body in white, but we deactivated all the modes. That's something we could do in Simpeg. So we ran these three body in whites um, in using three simulations, three ride simulations, and compared the results again for the damper top mount, Z accelerations. And what we found was this RT flex body or the real-time flex body showed good correlation. So what you see here, black is the full flex body in white with all the modes enabled, dynamic modes enabled. Um, RT modes flex, which is 8 modes enabled, matches very well with the full flex body in white. And the red curve is of course the the rigidized flex body in white in this case. So all the modes deactivated. Okay. So once we were happy with this, we took this Simpag model onto our driving simulator. Um, so here still we were still using for the pink curve, we were still using the our Simpag's default uh, variable step size solver, of course. Um, then we took the model to our real-time simulator, which is a static simulator, and we logged some data while we drove it on the same rough road patch. And what we see here is that we had very good correlation. So the green curve here is the curve which was logged with our from our real-time simulation, and that is compared to the full flex body in white simulation, and is also compared with the red curve or the pink curve here, which was the same uh, RT modes flex body in white but ran in offline, ran as offline. So what we saw was a very good correlation, um, and this was really a great achievement for us, I would say. Um, and of course, we could see the correlation here. Some info on our driving simulator spec that we have got in our Warwick office. It's a so we call it Simulia Simpac real-time driving simulator. The Simpac version that was used here is it's already quite an old one, but quite a powerful one, 2023 X.4 iHawk. Um, Red Hawk version 7.5, so CentOS 7.5.15 was used, which is at 3.9 gigahertz. The road used was the Belgian Pave .crg file, so we were using a CRG file here. Um, the SIMPAC model included ABS and ESC as an FMU that we imported. So this controller was developed a long time ago back using Demola. And then from Demola, it was exported as an FMU, and we included this into SIMPAC. So visuals, if I show you here, this is using SIMPAC animation. So this is the SIMPAC GUI, what you see here, and this is the model which is being driven in real time. Um, and that's me driving it using a simple Logitech steering wheel and the pedals at this point in time. Okay. So again, we ran with 1 millisecond using the fixed step size solver, linear implicit solver. Okay. And the SIMPAC model was run using 7 cores. So all of these 7 cores were from. So this machine had two physical CPUs, and each CPU had 8 cores, and we were using 7 cores on one physical CPU to run this model. And the real-time factor that we achieved with the flex body invite was average was around 0.871, was stable, and there were no overruns in this case. Um, in terms of the conclusion, I mean, I would have liked to show you more results on this one, but I didn't have it until that time, so I have not got. But temper top mount was one of the most important ones anyway. So flex body in white was able to run in real time up to second ride comfort. So there was a good correlation we saw between full flex body in white offline simulation and RT modes flex body in white real time simulation. Um, Real time factor was well below 1, which means this is very important. So the real time factor, which was coming out to be 0.87, so it should always be less than 1. Um, the fact that it was 0.871, which means that we could include more model fidelity into the model. Um, and so that was possible. Um, of course, users in this case, we were able to make changes in the model and run in real time immediately. So of course, if you remember, in terms of the requirements, the main requirement was that we should not be simplifying the model in any way. So, which means that we had the same component-based model running in real time, which means that you could change any hard point or any bushing property file or spring and dampers. You could even swap components as well. So this was quite a strong advantage that one could get out of these component-based real-time simulations. Um, yeah, so basically interact with the model in real time. Um, I've shown here ABS and ESC. So one thing what we can do is we can sort of in real time, so on the fly, basically while you're driving, you could enable or disable, for example, in this case, ABS or ESC. So the driver could immediately feel the difference, what's happening when you enable or disable the ABS and CSC. And we could do it using an Android tablet. So sending UDP signals from the Android tablet to enable or disable the ABS and ESC. So the driver will feel the difference immediately. And of course, it's quite well understood that this allows for much more agile approach in vehicle development than traditional methods. Traditional methods being either running just offline simulations or even having a full fidelity model, simplifying it, and then recorrelating it, and then running it on real-time simulators. So this method allows for much more agile approach for vehicle development. Um, in terms of the future work, so include results from simulations with higher fidelity tires. So I mean, I ran this model later on with CD tire, which is a much more higher fidelity tire model um, than TMEZ um, at that point in time, at least. And we could run the tire models or the tire instances on separate processors as well, so that sort of uh, distributes the calculation power better. Uh, so I should include those results as well in the future. Then do some parameter variations to improve the ride comfort. So now that we have got a model that can run in real time on a rough road like the Belgian Pavé, uh, we could think about doing some parameter variations like damping or including even air springs into the model to improve the ride comfort. So that's the next task. Include more flexible bodies, of course. We are getting a real-time factor with this model as 0.87. We could think of including more flexible bodies. Um, uh, so that's always possible, like the flexible suspension or suspension components. Include active systems like active dampers, include air springs, of course. Run on more capable hardware. So, of course, if I had more higher processing power, I could add more and more fidelity into the model as well. Um, and yeah, I mean, use more precise force and torque feedback, steering wheel and pedals. Example, sensor, the steering wheel and pedals from sensor drive. So we have got this into our office, but I've not um, I've not used it yet on my model. So this is some of the future work that we 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 understand that we should do on this model and see how it looks and compare the results, basically. So yeah, that's really it from my side on this presentation. So this is just another example running on the Millbrook rough road here. So this is the same Ford Taurus model I'm running on Millbrook surface. So you will see in a second the the model as well on the top screen. So these visuals are sort of from rFactor Pro. Here's the Ford Taurus model with the flex body in white. So this is the Simpac animation, what you see here. Also a feature that we have in Simpac. And I mean, we try to zoom into the real-time factor. This is the real-time factor. It's still around, you can't probably see it correctly, but it's around 0.87 as well, 6.7 as well on this one. And yeah, so if you have any questions, we are 20 minutes from 5 o'clock in the UK. So if you have any questions, then yeah, happy to answer.